Hello everyone. Welcome to section 10.4 on phase diagrams. The learning objectives for this section explain the construction and use of a typical phase diagram, use phase diagrams to identify stable phases at given temperatures and pressures, and to describe phase transitions resulting from changes in these properties, and describe the supercritical fluid phase of matter. As promised, we will continue to talk about phase changes here. So what we're doing here is we are taking into account several factors in looking at when phase changes occur. And I say several, it's basically two, pressure and temperature. We saw earlier that as we look at vapor pressure and we look at the point at which the vapor pressure equals atmospheric pressure as being the boiling point of that liquid. So we can imagine we could have we could reach the boiling point by either changing the pressure or the temperature. There's two variables there, and we want to be able to keep track of which physical state we have, given that we can change two variables. And a phase diagram is a way of doing that. So in a phase diagram, we keep track of pressure and temperature and which of these physical states we have. And we're showing an example here of a phase diagram. This is just a sort of, I would say, generic one. We're not saying which substance we're looking at here. In a minute, we'll look at some specific substances. So let's talk about what this diagram means. So over here, we're showing pressure. So as we increase pressure, what do we have occur? And over here we have temperature. As we increase temperature, what do we have occur? And so when we have higher pressure, you'll notice that for the gas phase, as we increase the pressure, we'll either go towards either a liquid or a solid. Likewise, we have increasing temperature. As we increase temperature, we'll go from solid to gas, solid to liquid, or liquid to gas. So you can see on this phase diagram where we have indicated those phase transition. So for example, here we're showing solid to liquid. We're showing, okay, when we go from solid to liquid, that's melting. When we go from liquid to solid, that's freezing. Over here we have liquid to gas, we have vaporization. Going from liquid to gas, we have condensation going from gas to liquid. And then down here we have sublimation going from solid to gas, and deposition going from gas to solid. So you want to be able to recognize this diagram in terms of when we have pressure on the y-axis and temperature on the x-axis, which physical state is in which part of the phase diagram. So you might need to know, maybe you're not provided solid, liquid, gas, you would want to be able to figure out what those would be. And then for each of these lines, which phase changes are represented by those lines, and how we would have a phase change occur by crossing those lines. There's a few other things I want to mention on this diagram that we haven't talked about yet that haven't been something we have talked about before. So we've actually talked about all three of these physical states and all three of these pairs of phase changes already. Before we move on to that, though, there's one other thing I want to mention. So each of these phase changes that we're showing with these arrows are phase changes because of a change in temperature. Okay, so we know that because if you look at the graph, the x-axis is temperature and the line is going parallel to the x-axis. All of these lines are parallel to the x-axis. We could also, in some cases, cause a phase change by changing the pressure. So those would be vertical lines. So we could have a vertical line here where let's say we lower the pressure of a liquid and it starts to boil, and we have a phase change from liquid to gas by lowering the pressure. Similarly, we could lower the pressure of a solid and potentially have a phase change to the gas phase. So that's another thing that we could look at on this graph in terms of phase changes. We've mainly to this point focused on phase changes because of changes in temperature. We can also sometimes have phase changes because of changes in pressure, although that is not always going to be the case. Okay, so there's two additional things on this graph that we haven't talked about yet. So let's go ahead and talk about those. One of them is right here. This is called the triple point. The triple point is a very specific temperature and pressure for a substance. And at that very specific temperature and pressure, that physical substance can exist in any of the three physical states. It could be a solid, it could be a liquid, it could be a gas at that location. So it's a very specific temperature and pressure called the triple point. With pressures above the triple point, we go from solid to liquid before we go from liquid to gas. Whereas when we have pressures that are below the triple point, we would go from solid to gas without going first to the liquid phase. So there is a pressure for any substance below which sublimation will occur. It just so happens that for things like water, that pressure is lower than atmospheric pressure, whereas for things like carbon dioxide, that pressure is higher than atmospheric pressure, which is why we can see for carbon dioxide it goes from solid to gas without becoming a liquid. But if we were to do that at a higher pressure, we could see liquid carbon dioxide. The other point we haven't talked about yet is this one, and it's called the critical point. The critical point is the point beyond which you don't actually have a distinction between gas and liquid. That might seem a little bit odd that would happen, but if you think about what we're looking at here, we're looking at high pressures, and if you have a high enough pressure, at some point you can't push the gas molecules any closer together, and they start having to be right next to each other regardless of what the temperature is. So beyond the critical point, there isn't this distinction anymore, and we have something that has some characteristics of a liquid, some characteristics of a gas, that we call a critical fluid. So they have a very high density, but at the same time, they are filling the space of their container. So beyond the critical point, we don't have that distinction. There aren't any common substances that have critical points anywhere close to atmospheric pressure. I don't even think it's possible to have something with a critical point at that pressure. So this is something that people that do specifically this kind of experimentation will look at. Okay, so let's look at before we look at a specific example, one other thing I do want to mention here. So we talked a little bit about the pressure, how we can change pressure to cause a change in the physical state in some cases. So let's talk about that a little bit more. So for a gas, if you were to increase the pressure of a gas, you might form a liquid. And then if it's at a lower pressure, you might form a solid by increasing pressure. I'm sorry, if it's at a lower temperature, you might go from gas to solid by increasing pressure. At a higher temperature, go from gas to liquid by increasing the pressure. There's another possible one, which is between solid and liquid. So this one is not always as obvious. Do you increase or decrease the pressure to cause that change? So if we look at this particular phase diagram, increasing the pressure could cause a liquid to become a solid. Now you have to be really close to this line for that to even be a thing, but increasing pressure causes a liquid to become a solid. Now, this is not true for all substances, and we'll see an example of that shortly. But the basic idea is that if the solid is more dense than the liquid, which is true for most things, increasing pressure when you are really close to the temperature of the phase change can cause a liquid to become a solid. Let's look at an exception. The exception is the one that's always the exception. It's water. Water is an exception to this. So if you compare this phase diagram to this phase diagram, so this one has specific numbers on it, one of the things you'll notice is that the phase diagram on the top, the solid liquid line is angling up to the right, whereas the solid liquid line on the water phase diagram is angling up to the left. Okay, so that is a difference between them. And water is not unique, but it is odd in having this characteristic. There are other things that have a denser liquid phase than solid phase. So for water, if you were near this temperature line, near the solid liquid line, if you were to increase, if you had a solid and you increase the pressure of this solid, you might be able to form a liquid under those cases. So it's different in that regard. There's actually a few implications for that difference. One of them I'll go ahead and mention. Because liquid water is more dense than solid water, that means that ice floats. Now we all know that ice floats, right? So that's why that is occurring. However, if ice did not float, what would happen is all of the oceans would be basically ice because they would never thaw at the bottom when the ice went to the bottom. So very important for life on Earth, the fact that ice floats on water, which we can see from the phase diagram. A couple other things I want to point out here. There are some specific numbers shown here. So the units here are kilopascals, which we haven't normally used kilopascals. We normally use atmospheres. So 101 kilopascals is 1 atmosphere. And at that pressure, you can see, okay, that's the normal boiling point of water. So we can see that. And then you can also see on here the normal freezing point of water of 0 degrees as well. And this, as this changes, that could change a little bit. Now also note, just look at the range here. This one is not really to scale. So we're going from 0 to 0.1 and then to 100. Although this line does kind of angle to the up to the left, it is not as much as this is showing. So we're showing that just so we can see that that's true, but we're basically over zooming in on this part compared to the rest of the graph. Also, we're showing what the triple point is. So the triple point is 0.01 degrees Celsius and 0.6 kilopascals. So it is very close to, the temperature is very close to the freezing point of water, but it's a very low pressure, very, very vacuum conditions for that to happen. So it is possible to do that. And then we're also showing what the critical point is. So the temperature is actually not that high, 374, but it is a very high pressure at the critical point. I want to contrast this with another one, and then we'll be done with this section, and that is for carbon dioxide. So in carbon dioxide, we see that we do have the liquid line angling up to the right. So again, solid more dense than liquid, as we would expect for most things. But then also we see that we have a much lower triple point in terms of the pressure. So I'm sorry, I said that backwards. We have a much higher triple point compared to the pressure. So 101 kilopascals would be atmospheric pressure. We're above that. So we have to have a higher pressure in order to have liquid carbon dioxide. However, to get to a supercritical fluid, this pressure is much lower. So it's about 100,000 kilopascals, or I'm sorry, 10,000 kilopascals compared to for water, it was 22,000, okay, kilopascals. So it's a more modest location. You don't have to memorize any of these numbers for actually for either carbon dioxide or water, other than the normal boiling and freezing points of water. But there's a lot of research being done and actually practical applications of using supercritical carbon dioxide. So that is it for section 10.4 on phase diagrams. Please make sure you understand this before moving on to the next section.